For following rules of nomenclature, it's easiest if we can classify compounds based on what the type of chemical bonding looks like in that compound. So in this example, we're going to name some chemical compounds from their chemical formulas, and we're also going to write down a chemical formula given a name. You'll notice that the first thing I've got to do is classify each one. I'm just going to do this to make it easy on myself. I'm going to recognize that the compound in question number 1 is a covalent compound because it consists only of elements from the right-hand side of the periodic table, nonmetals. Likewise, compound number 2 is covalent. Compound number 3 consists of a metal and something we recognize from our polyatomic ions list. This must be an ionic compound because it contains ions. Likewise, for compound number 4, a metal and a nonmetal. Here we've got to keep in mind that the metal that we're dealing with is part of the D block. So we give special names to D block elements that form cations. Just like in question 4, we find another D block element in question 5. In question 6, we're dealing with a substance that's ionic but contains a hydrogen cation and is an aqueous solution. This signals to us that we're dealing with an acid. Acids get special names. Likewise, question 7 contains an acid. I'll fill out the rest of the chart now. Here we are. In order to name covalent compounds, we say how many of each element are present using prefixes. In question 1, there are 3 carbons. The prefix for 3 is tri, so we call this tricarbon. There are 2 oxygens. The prefix for 2 is di, and we always end the second element's name in IDE, so we call this tricarbon dioxide. Question 2 is also covalent. When there's only one of the leftmost element in a covalent formula, we don't use any prefix at all. We just call it its element's name, iodine. There are 7 fluorines. Prefix for 7 is hepta, so we'll call this heptafluoride. For ionic compounds, we name by saying the name of the cation and then the name of the anion. The name of the cation is rubidium. The name of the anion is carbonate. That whole cluster of CO3 with a 2- charge is a polyatomic anion. In question 4, where we're dealing with D-block transition metal elements, we need to identify the charge of a cation in order to name it. The charge of our anion, sulfur, is 2- based on its position on the periodic table. There are 2 of them, so altogether, all the sulfurs contribute 4 negative charges. The sole tin must contribute 4 positive charges. So we name this tin 4 sulfide using Roman numerals. Similarly, in question 5, we can identify from our chart that cyanide is a -1 anion. There are 3 cyanide clusters, therefore 3 negative charges overall from all the cyanides. Our sole gold must contribute 3 positive charges. This must be gold 3 cyanide. We name acids that contain oxygen using adic-itis. In this case, our polyatomic anion that brings hydrogen to solution is called chromate. We change the ending ate to ic or the ending ite to ous in naming an acid and call it an acid. Chromate, as an acid, becomes chromic acid. When there is not oxygen present, we name an acid based on the template hydro blank ic acid. The thing that fills in the blank is the root word for the anion that brings hydrogen to solution. In this case, the hydrogen is brought to solution by a phosphorus anion, phosp, and we call this hydrophosphoric acid. I'll fill out the remaining names now. When we write down chemical formulas from names, we work our way backwards. Ionic compounds, including acids, get their formulas written based on a charge balance, showing an equal number of total positive and total negative charges. A covalent compound has its formula written based on the total number of atoms of each type implied. Acetic acid, for example, must contain the acetate anion, working backwards from atic itis. Acetic, with no hydro prefix, must have resulted from acetate. Acetate is the same chemical formula as in question 10's anion, C2H3O2 with a -1 charge. Acids also have to have hydrogen cations, H pluses, in their chemical formulas. We only require one H plus for every one acetate anion to balance charge. The formula for acetic acid is HC2H3O2, and we'll specify that it's an aqueous solution. Potassium permanganate is an ionic compound. Potassium is K+, according to our chart of polyatomic ions. Permanganate is MnO4 with a -1 charge. We only need one potassium cation for every one permanganate anion. In calcium hydride, calcium is our cation. It's got a 2+ charge. Hydride suggests that we have H-. In this case, we need 2 hydride anions for every one calcium cation to balance charges. Its formula is CH2. In question 14, we're explicitly told the charge on our cation because it's a D-block element. Vanadium with a 2 indicates that we must be dealing with vanadium 2+. Bicarbonate, according to our chart, is HCO3 with a minus charge. In order to balance charges, we need to have 2 of this entire cluster of HCO3. To demonstrate that we have 2 of a cluster of a polyatomic anion, we'll put parentheses around that ion's formula and indicate a subscript outside. In question 15, where we're dealing with bismuth 5, we again have a D-block element whose charge is explicitly specified. Bismuth must be +5 in this case. Nitrate is NO3 with a -1 charge. And the formula for bismuth 5 nitrate is BiNO3 5. For rubidium peroxide, we're dealing with rubidium with a +2 charge. We're dealing with peroxide, which is, according to our chart, O2 with a 2- charge. In this case, we need 2 rubidiums to balance the 2- charge on that peroxide polyatomic anion. In question 17, for a covalent compound, we don't have to worry about charges at all. We just write down how many of each element our name suggests. Diphosphorus suggests 2 p atoms. Tetrafluoride suggests 4 f atoms, P2F4. Again, hydrofluoric acid must contain hydrogen as a cation. In this case, the prefix hydro means that we're just dealing with the anion whose name is suggested by fluor. That's fluoride. Fluoride is a -1 anion. Hydrogen is a +1 cation, so hydrofluoric acid is just HF. Again, in question 19, a covalent compound, tetraiodine, suggests 4 I's. Non-oxide suggests 9 O's, I4O9. Lastly, in question 20, ammonium hydroxide, 2 polyatomic ions. The first, a cation, NH4 with a +1 charge. The second, an anion, OH, with a -1 charge. We just require 1 of each ion to balance the overall charges.